Quantum physics says that objects can be in two places at the same time. A group of physicists now says that they can also be at two times at the same time. That time can run both faster and slower, and that we can actually measure this. If they are right, then time is not what we think it is. Your brain is literally experiencing different times at once, though the difference is too small to notice. Let's have a look. Time is a big headache for physicists. The issue is that in different areas of physics, we treat time in a different way, and these different treatments don't fit together. Importantly, in Einstein's theory of general relativity, the passage of time depends on how you move. The more you accelerate, the more time slows down. If you, for example, try to hover near a horizon of a black hole, you must constantly accelerate a lot just to stay there. This is why time runs so slowly near a black hole. You can also slow down time by running in circles, which you can experience for yourself by training for a marathon on an indoor track. That is time in Einstein's world. But in quantum physics, time is somewhat confusingly actually more like what we intuitively expect it to be. It's a sort of universal clock, an external parameter. The trouble with this different treatment of time becomes apparent if you try to combine the two theories. Even before you actually try to build a quantum theory of space and time, if you just so much as use the symmetries of Einstein's theory in quantum physics, then time disappears completely. That's not ideal. If your maths eats time, then how do you explain this? So the authors of the new paper do something different. They say, okay, look, let's just take it seriously that the passage of time depends on the motion of an object and use this as a minimal connection between quantum physics and relativity. Usually the effects are tiny and you can get away with pretending there is only one time for everything. But sometimes tiny effects are measurable, for example, in atomic clocks. The authors say, look, in atomic clocks, the atoms are in a superposition of two different states of motion. And if time can also be in a superposition, then this should become measurable. To measure this, they don't want to use a standard atomic clock. The most widely used atomic clocks use clouds of cesium atoms. The authors instead want to use what's called a single ion clock. As the name says, this works with only a single ion, and concretely they want to use aluminium ions. Why aluminium? Because these have a transition in the optical range, which gives a better precision than cesium. The clocks work by using a laser to zoom in on the atomic transition. From the frequency of the transition, one then extracts a time standard. Cesium has a transition in the microwave range, so at longer wavelengths, which gives lower precision. Cesium atomic clocks are currently used mostly for historical reasons. They were developed in the 1950s, and back then they had many things: Elvis Presley, radioactive toys, an obsession with pastel colors, but they didn't have optical lasers. The first microwave lasers were developed around the same time as atomic clocks, but their accuracy wasn't great, so they used other microwave systems. Now, 70 years later, the second is defined based on the cesium standard. We'll probably switch to a different definition of the second in 2030 or so, which will have a higher accuracy and be based on an atomic clock with an optical transition. It's these up-and-coming high-precision atomic clocks that the authors of the new paper are looking at. They are not saying that the issue with the multiple times would ruin the clocks, rather that one can use the clocks to see whether the multiple times really exist. They say one has to prepare the aluminium ion in a specific quantum state that can be achieved with, guess what? More lasers. Then this one quantum state contains multiple different motions of the ion, and each has a different time. This then leads to a blurring of the clock's precision. This effect, if it exists, is quite similar to the reason why Roger Penrose thinks that gravity causes the collapse of the wave function. He says, look, the gravitational field of an object itself causes an acceleration. If an object is in two places at once, then these are two different accelerations because they point in two different directions. But now the object, since it's in two places at the same time, has two accelerations accelerations and hence 2 different times. If a quantum object is heavy enough, then this alone will quickly ruin the quantum behavior. The difference to the effect that the authors of the new paper want to test is that Penrose says the acceleration comes from the gravitational pull of the quantum object. The new experiment with the atomic clock would instead look at the acceleration caused externally. So it's not the same, but they are related in spirit. I give this paper a 3 out of 10 on the bullshit meter. It's correct, and it's a neat idea, but I think testing Penrose's ideas is more promising. Still, I like the idea. The next generation of clocks may not just tell us what time is, it may tell us how many times it is.